Hey guys, welcome back to Physics with Miss Whiteley. Today we're going to be talking about measurement units and the guess method. Now these things are all semi-related, but they are topics that we're going to be using pretty much every day in physics. We're going to be using measurements of some sort. We're going to be using units all the time, and a lot of times when we use math, we're going to do the guess method. So all of these things are very foundational for the rest of this physics course. So it's kind of important that you get them down. Now, the first of those things was measurement. And measurement is all about figuring out what's going on in the world around us, because that's the goal of physics, right? And in order to do that, we have to make observations. And there are two types of observations. There's qualitative. I always have to pause and think about how to spell qualitative. But the root word of that is quality. And there's also quantitative. Sounds really similar. Spelled really similar, but the root word of that is quantity. So you've got quality and quantity, and you might have heard the saying before, quality over quantity or quantity over quality. You know, it goes both ways. But the key difference in these is whether they're described with a number or not. So qualitative just describes some property that you can't express as a number. Quantitative, that's the root word quantity, which means a number. Those are observations that can be expressed as a number. So, for example, when I'm in the classroom and I'm not teaching online, I like to say a qualitative observation about the classroom is that my desks are black, which is for the most part true. I have a mixture of types of desks, but most of my desks are black. And that's not described numerically. That's just an observation. But quantitative could be something like, my desks are 4 foot wide or long, I guess you could say, depending on how you want to describe that measurement. But 4 feet is a quantitative observation because it's got a number there. Some more observations you could make would be on the qualitative side. You could say the desks are stiff or rigid or hard, as many student who has tried to sleep on them would tell you. Desks are hard. Another quantitative thing you could say is I have 25 desks in my room. Let's see, something else we could say. Somebody had this in class today. Clocks are round. That is a qualitative observation. Talking about the clocks in my room, they are round. A quantitative measurement that we took today was the time. And actually right now this is 10:01 p.m. Shouldn't be doing this at this hour, but here I am. So it's 10:01 p.m. That's a quantitative observation because it involves a numerical value. Okay, so that's the difference between those two types of observations. But today we are looking specifically at measurement. And measurement is the act of taking a quantitative observation. That's what measurement is. You're taking a quantitative observation. And so what we did today in class, if you weren't here, that's probably why you're watching this video, is we measured the length and the width and the height of the room using meter sticks. The end goal of that was to figure out how many pounds of air were in the room, and maybe you'll get to do that when you come back to class because some of our classes didn't finish. But measurement was the act of finding those numerical values. Like the length of the room was around 13 meters and the height of the room was around 3 meters. Okay, that's what doing measurement is taking that quantitative observation. Which takes us to our next topic. So our next topic is a little bit different. It doesn't really segue very well for measurement, but sometimes when we take measurements, they're really big numbers or really small numbers, and writing them can kind of be inconvenient. So scientists came up with this thing called scientific notation, where we write numbers slightly differently. It's a little bit of a shorthand kind of a thing. For example, the speed of light is approximately 300 million meters per second. So that's a 3 with 8 zeros and a meters per second on the end. Okay. Now, if you're calculating all the time and you're having to write that all the time, type it into a calculator all of the time, that can be a bit tedious. So what scientists have done is come up with this notation to shorten it. And that notation takes your first 3 digits, so there's 300, and it puts a decimal right after the first digit. So if you put the decimal there, you get 3.00. And then, to make it the same as that actual value, they multiply it by 10 to some power. And it's whatever power would make it the correct number. And it's also equal to the number of decimal spots you'd move over. So in this case, not sure if I did the right number of loopies there, but in this case, it would be moving the decimal 8 times. So you could write 300 million as 3 times 10 to the 8th meters per second. And 10 to the 8th is 100 million, so that's 300 million. That's the speed of light. Now you might say, man, that's not that inconvenient, not worth learning a whole new notation over. But things can get even crazier. So let's look at the mass of a proton. The mass of a proton is a decimal with 26 zeros, and I have to count them to be able to write the right number. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, and then the digits 1, 6, 7. And that's a little bit crazy. And it's also measured in kilograms. But that's a crazy number to have to write all the time. I don't know about you, but if I had to use that frequently, I'd probably miss a zero occasionally, type in the calculator wrong. And if I was having to do some calculations that someone was relying on for something, it wouldn't be a good idea for me to keep doing that. So the scientific notation solves that problem. And what you do is you take the same 3 digits, the 3 real digits there, 1, 6, 7, and you put a decimal after the first one. So you turn it to 1.67. And if you counted all those decimal places over, that would actually be 27 that it would have to move. Now, since we're moving the other way, it actually is times 10 to the negative 27th. And we'll talk about that in a minute. But that's way easier to write than all of those zeros and having to count them all out. So looking at these two numbers, there is a key difference in that exponent. You've got an 8 and you've got a negative 27. One of those is positive and one of those is negative. You've got a positive and you've got a negative. So it can be either. Either is valid for scientific notation, but they mean two different things. So thinking about those two numbers, the speed of light, which is very fast, and then the mass of a proton, which is a tiny, tiny little object, you might notice that the 8, or you might, infer that the 8 is going to be a big number. So the positive 8 means a big number. Positive power means a big number. But a negative power, like negative 27 for the mass of a proton, that's going to mean a very small number. So in your scientific notation, the sign on your exponent is going to tell you if this is really big or really small. Okay, speed of light's really big, it's got a positive exponent. Mass of a proton's really small, it's got a negative exponent. Now, when you're doing scientific notation, most of the time I'm not going to have you actually counting decimals. It's just going to come out in your calculator. And I can't really show you that super well right now. So either Google a tutorial for how to use scientific notation on the TI-84 or ask me when you get back to class. Now, moving on from scientific notation, we're going to get to units. And a lot of people think units, maybe not are ridiculous, but a lot of people don't like to use units. They don't think units are important. They don't care about units. So I would urge you to go at this point in time. I think I have it linked in Google Classroom. You can go to the notes material there in the Google Classroom, and you'll see a video about NASA and their $193 million satellite. And if you give that a watch, I think you'll see why units are truly important. And there are 7 of these units that are called the base units in the SI system, which is the internationally recognized system for units among scientists. There are 7 of these base units, and we're going to talk about what they are. They're listed here in this little table. For length, the base unit is the meter, and that's a lowercase m for meter. And then for time, it's seconds. That's a lowercase s. For mass, it's kilograms. I know in chemistry you probably used regular grams, but kilograms is actually the SI unit. For current, that's electrical current. It's the amp, which is a capital A, or you could write the whole word amp. Either one is fine, but amperes is the full word. For temperature, it's actually not Fahrenheit or Celsius. Many people think it's Celsius, but it is Kelvin. Kelvin is closely related to Celsius, and we'll learn about that at a later date, but it is actually a little bit better than Celsius for reasons that we will again get into at a later date. So that is Kelvin. And we also have luminosity. Luminosity is not one that we mess with a whole lot, but it's basically like the intensity of light, and it's measured in candelas, which is a CD as the abbreviation for that one. And the last one is amount of something. This one is your most dreaded unit out of chemistry. It is the beloved mole, M-O-L. Now, we don't really use the mole very much in this class, but it is one of the 7 base SI units, so we're going to include it there in our list. Out of these, the ones that we use the most are the length being meters, the time being seconds, the mass being kilograms, and then later on in the year we'll do current and temperature with the amps and the kelvins. The candelas and moles we don't really mess with a whole lot. Now sometimes measuring with these units can be not the best, right? If you want to measure something that's small, you don't really want to be measuring it in meters because a meter is too large to measure a small thing in general. So people invented these metric prefixes to go in front of these units to kind of scale them up or scale them down. We're going to fill in the chart first, and then I'll show you how the scaling works over there in the examples. So for the prefixes, the first one is giga, and the symbol for giga is a capital G. This is like gigabyte, and that stands for times 10 to the 9th power. So that's multiplying by 10 9 times. The next one up is mega. Mega is a capital M, and it is times 10 to the 6th power. We've also got kilo or kilo, like kilometer, and that is a lowercase k times 10 to the 3rd is what it means. Next up is centa. It's kind of the only one that goes out of pattern here. This is like centimeter. Centimeter is a lowercase c. And a centimeter is smaller than a meter. So what you would expect to see at this point is that exponent to start to go negative because now it is going to be smaller. We're looking for smaller numbers. So you get a times 10 to the negative 2nd on the centi prefix. After that, you've got milli, like a millimeter, and that is a lowercase m. It means times 10 to the negative 3rd. Next up is micro. Micro means times 10 to the negative 6th, but it's got a very odd symbol. It's the Greek letter mu, and we'll talk more about the Greek letter mu when we talk about friction, but using it with units, it stands for micro, and the symbol looks like a U with a tail in front of it. And people handwrite mu's differently. This is the way that I write it, and it looks pretty similar to the way it's printed. You can see it printed over in the examples in a minute. But that's micro. The symbol is a mu, the Greek letter, and it stands for times 10 to the negative 6th. And the last one is nano. That's just a lowercase n. It means times 10 to the negative 9th power. I just wrote 9. It's negative 9. Okay, 10 to the negative 9th power. Now the way that you use these prefixes, we'll see that over here in the examples. And it's really easy. The first one says 28.1 centimeters. We want to know what that is in meters. So all you have to do to convert is write down your exact same number. Don't change anything about it. 28.1. Okay? And then you got to look at your prefix. Your prefix here is a C for centimeters. And that C means times 10 to the negative 2nd. I'm going to highlight it so we can see. That means times 10 to the negative 2nd. That's the one we're doing here on this one. So now that we've got the times 10 to the negative 2nd, we just tack it on to the end there. So our answer is 28.1 times 10 to the negative 2nd, which is like moving 2 decimal places to the left or dividing by 10 twice. That's going to really convert you to meters. You can type it into a calculator and check me if you want to. But you do the same thing for the other ones. We've got 3.7. Mu stands for micro, so that's 3.7 microseconds equals blank seconds. I'm going to highlight again so everybody can see. This is our question. Mu is our unit, or sorry, is our prefix on the unit. So we're going to be on the micro line there, which is 10 to the negative 6. So our answer here is just 3.7 times 10 to the negative 6th. Cool. Next up, we've got 6.8 milliamps. Okay, I'm going to highlight this one as well. So we're on the milli line for this one. And that is 6.8 milli is times 10 to the negative 3rd amps. Next line, 5.15 nanometers. Got to highlight again. There we go. That's going to be 5.15. Sorry, I just wrote the wrong thing. There we go. 5.15 times 10 to the negative 9th for nano. And then last one here is the kilogram. The kilogram, I got to find my last highlighter color there. The kilogram means times 10 to the 3rd. So the answer here is going to be 1 times 10 to the 3rd, which is 1,000. And you might already know 1 kilogram is 1 times 10 to the 3rd grams, or 1,000 grams. Okay, moving on. We have the guess method. Okay, now the guess method is maybe the most important thing out of this whole shindig, all right? Because this is going to get used practically every day for the entire rest of the year. And to teach it to you, I've just got to show you an example, okay? And the example involves an equation. The guess method is how to use an equation to answer a question. And so to do that, we need an equation. We're just going to use the density equation because you learned it in chemistry, and you probably also learned it in 8th grade. It says density equals mass divided by volume. And then we're going to try to answer this question. This question says, if a human has a density of 1,000 kilograms per meters cubed and a mass of 62 kilograms, what is the volume of the human? Kind of a weird question, I know, but roll with it. So the guess method, GUESS, is the acronym. It stands for Given, Unknown, Equation, Substitution, Solution. And you can see that down here. So what the givens means is you need to look in the question and see what information you're given. And that's usually going to be a number. There's sometimes a few hidden givens, but we'll talk about those when we get to real physics questions. But here in this, we're just looking for numbers. So our two numbers that we have are 1,000 kilograms per meter cubed and 62 kilograms. Now you got to use some context clues here, but if you look in the question, it tells you what each number means. This 1,000 kilograms per meters cubed is density, and that's the capital D. Density is 1,000 kilograms per meter cubed. And then it also tells you this 62 kilograms is the mass. So that's going to be the M, 62 kilograms. Now what we're looking for is the volume. It says, what is the volume? Okay, so that's the givens. Givens were the two numbers, and then the unknown is figuring out what the question wants to know. So what it wants to know is that volume. So now we've done the givens and the unknowns. We got to move over to the equation, substitution, solution side. Now later on in physics, we're going to have lots of equations to choose from, and part of your physics skill is going to be knowing which equation you need to choose. Now today we've just got one, and it's the density equals mass over volume. So that's what we're using. And we can go ahead and move on to the substitution portion. Substitution here just means you're going to plug in numbers. So what we're going to look at here, I'm going to zoom in a little bit, is plugging in the correct numbers. Now if you've already got it written down, and you should, density was 1,000 kilograms per meter cubed. So I'm going to plug that in for density. Now you don't really need the unit. Sorry, other physics teachers out there. You don't really need the unit, at least for this class, for the on-level. So you can just put the number 1,000 for the density, equals the mass. Mass we knew is 62, divided by the volume. And that's what we're looking for. Now, if it's the thing you're looking for, like the volume, you can't plug in a number because you don't know. So all you do is plug in the variable, the V. And now what we got, can't talk. Now what we need to do is find the solution, okay? So we got to solve this for V. And that's where your algebra skills are going to come in. You're going to need some algebra for this class, and I'll help you out with it as we go. This is one of the harder algebra solutions, and the main reason for that is because v is on the bottom of a fraction. And you can't directly solve for something that's on the bottom of a fraction. So we got to get it out of there. Right now, it's being divided. We've got 62 divided by v. And to get it out of there, we have to undo that, or do the opposite, or the inverse. That's multiplication. But what we do to one side, we have to do to the other. So we multiply v on both sides. What that does is it cancels this one out. And now we've got this equation, v times 1,000 equals 62. And the last thing we need to do is get v by itself over here on this side now. And it's being multiplied by 1,000. So to undo that multiplication by 1,000, we're going to divide by 1,000 on both sides. So we've got the volume equals 62 divided by 1,000, which is 0.062. And the unit on that ends up being meters cubed. Okay, so that solution with algebra was the last little piece. And that's the whole guess method. So with the guess method, you can solve pretty much any mathematical equation. And you've got to practice to go work on that with. So we're going to have a practice over this. The answers to the practice are in Google Classroom, so you can check yourself to make sure you're getting them right. And if you're getting them wrong, you can come ask me questions. The algebra on those is a little bit tricky. It is some of the harder algebra out of this class. I want to kind of go ahead and get it out of the way, finding those algebraic solutions. So go have a crack at those, and then there will be a quiz waiting for you when you get back to class. I'll have to post, or I'll either post the password for the quiz or you can come ask me about it. But let me know if you got any questions. Thanks for watching.